Okay, so last time we were talking about Gauss's divergence theorem, and we motivated it. We did an example, and then I got to some physical examples, and the one that we had time to talk about was light bulb. And I think this is a really nice starter example because it really brings to life this suggestion that I've made in the past that even though you measure flux on the boundary, and as such, it's tempting to think of it as being on the boundary, coming from the boundary. I mean, that's where it is, it seems to be, because that's where you measure it. It's really easy to motivate from this example that no, all the flux that you measure on the boundary was flux of photons, and all the photons came from the light bulb. They came from the LED there at the center, right? So this really underscores my persistent suggestion that we think about boundary flux as actually coming from the interior, not from the boundary itself. Okay. All right, so I want to do another example here. Now, before we get to the other example, I should point out certain assumptions in the light bulb examples. So the fluid is being generated. Not all fluids are, right? Some fluids are just kind of there. And aren't actually being sort of, created in time. Light bulbs are literally generating the fluid here, the fluid being made up of photons. Okay, another thing I'll remind you of. The density does not change over time. The density is independent of time, you might say. You can also say constant, but let's also recognize that, the density is spatially dependent, right? There's more photon density there, and there's less photon density over here. But as far as time is concerned, the density of the fluid is constant. Okay, so the fluid's being generated, but the density is constant. We're about to look now at an example, fluid flow example where that's turned around backwards. All right, so here we go. We're going to think about let's say a gas, and let's imagine that there is a balloon. I'm going to draw a large balloon here, and there's a constant density of gas inside of that balloon, and then imagine that the balloon starts to expand. Right? As the balloon gets bigger, well, some of the gas is going to have to go out with the balloon, right? And I argue that gas that's further away from the center will be moving faster, and gas that is closer to the center will be moving slower. After all, the gas that's at exactly the center will not be moving at all. The gas that's on this side will be moving to the right, and the further you go in that other direction toward the other side, the faster it'll be going in that other direction. So, just a plausibility argument, but this is what will describe that flow of gas. So let's think about what can we say about this fluid flow. First of all, there's no generation of fluid. There's not a light bulb spewing out photons here, right? The fluid itself is kind of fixed. There's only so much fluid, period. Nothing's being generated. But is the density constant? Oh, nonsense. No, the density is decreasing. There's a finite amount of gas that's inside of this balloon, and if the volume is getting bigger, the density is getting smaller. Right? So this is a very different kind of a fluid than the light bulb example that we just got through looking at. Okay, now, we can still write down the divergence theorem. We can still ask, what does this mean? How do I interpret the quantities involved? Real quick, let me point out that the fluid flow itself being known, right, there's our fluid flow formula, and you can compute the divergence of that, and it ends up being 3K. I want to remind y'all there is a formula for divergence. Make sure you know the formula. Make sure you can compute that. Keep in mind this vector field that I have represented here. I have it represented kind of vector notation. In order to compute the divergence, you'd need to write that in coordinates, because the formula we have for divergence is kind of in terms of the coordinates, the components of the field. Okay. All right. So, what sense do we make out of this? So we've got flux on the left. That's measuring how much fluid is leaving our region. So we do have an expanding balloon, and that's true, but we're focusing our attention here on a fixed sphere. And as the fluid sort of expands outward, some of the gas is passing through our sphere. Right? So flux just says how much fluid is leaving the ball by way of course, the sphere, passing through the boundary of the ball. Okay. All right. So, so this flux represents an amount of fluid that we are losing. So, when I say that is a triple integral of divergence, what does the divergence here represent? This divergence is representing how much of that flux that we measure on the boundary is actually originating in any given region. So specifically, by virtue of being a constant, you'll notice right here the divergence is constant. It's just 3 times K, whatever that constant K is. What that's telling you is that the fluid that is leaving through the boundary is coming in some sense uniformly from everywhere inside of your sphere. So if you think about the sort of the arithmetic of it all, we've got a certain amount of gas inside of our sphere. As that fluid starts to leave, there's less and less gas inside of our sphere. The density is still uniform, though. So that means that inside of this sphere, there was a density of gas at some uniform density of gas at some level. And as gas starts to leave, that density uniformly decreases. Right? It was uniformly at this level, and as the gas leaves, the density decreases. And the fact that this is a constant is what's telling you that you're getting a constant rate of decrease of density everywhere throughout the balloon. All right, so this is a very different interpretation of divergence, and this different interpretation is necessary because, of course, it's a very different kind of fluid. This is not a generated fluid like photons, right? But it's also not a constant density fluid like photons. So just got to interpret accordingly. Now, the 2 examples that we've seen are kind of extremes on a spectrum. I want to point out that sometimes, depending on the fluid, and I don't want to get off into examples and worrying too much about this kind of stuff. This is more engineering than what we have time for in this course. But I just want y'all to be aware that you might have both of these. You might have a fluid that is being generated, like the photons example, but also where the density of the fluid might also be allowed to change for whatever reason, depending on the nature of your fluid. And in that case, this is what I argue is going to be the starter sort of, first equation to write down. And I argue it as follows. If fluid is being generated, let's just think about the 2 possibilities of where that fluid could go. There's really only 2 possibilities. One possibility is that as I'm generating fluid, that fluid could be leaving my region. That's what flux is, right? So to the extent that as I generate fluid, that fluid is leaving my region, that's contributing to flux. On the other hand, there is another possibility. As I generate fluid, it might be not leaving my region. And if I'm generating fluid that doesn't leave my region, then I'm increasing the total amount of fluid in the region. So those being the 2 possibilities, all of this generated fluid, it's got to go to either one or the other of these, and therefore the sum on the left is equal to the quantity on the right. Now thinking per unit volume. Flux per unit volume is divergence. Mass per unit volume is density. And okay, now this generation rate, this is a kind of a new concept, quantity of fluid per unit time. If I were to then say per unit volume, I think generation rate density, because of the per unit volume, would be a reasonable way to think of this. But that's, again, I don't want to get too much into the particulars and specific examples. It's not really what this course is about. Punchline, though, divergence, again, tells you information about these two things that I might be interested in. And what I know, once you know divergence, what you know about one of these remaining quantities will tell you the other. So, all right, again, not really what we want to focus on in this class. I just wanted you all to see that there was a way to connect these examples. Okay, now, another physics idea. This one, very important, gravitational fields. Big deal. Now, we have already written down the gravitational field for a point mass. We wrote this down in chapter 3, right? I described it as inverse square radial because, well, after all, inverse square, you can see right there, and radial because the direction, that unit vector direction, is always radially outward from the origin. Okay. All right, so I hope that looks familiar. Here's what I did not tell y'all back in chapter 3. Now that we are into the divergent stuff, this is more appropriate time to bring this up. But it's just like our photon example. If you were to write down the vector field describing how the photons flow, and keeping in mind the factor of density, when you write down a vector field representing a fluid flow, if density is not a constant, you should have a factor of density in there. You get exactly this, as it turns out. All right, now this is weird. This is counterintuitive. After all, light and gravity do not seem to be the same thing, right? So it's a little bit of an eyebrow raiser when very, very different physical quantities are algebraically so closely related. So here's what we do with that. There is a speculation, and I'm not going to comment on how well believed this is, because for one thing, I'm not an expert in this area, and for another thing, it doesn't matter to what we're doing. But there is a physical theory that gravity is actually communicated by emitted particles, just like photons are what communicates light. That there are little particles called gravitons that communicate gravity. And specifically that the gravitons are being created and hurled outward by mass in the same way that photons are created and hurled outward by LEDs, light bulbs, things like that. That's theory. It fits perfectly with the algebra. Said differently, if this theory were true, I'm not saying that it is. If this theory were true, then you would get a vector field that looks exactly like this, which is exactly like what we physically observe in the physical universe. So the reason I say that we kind of don't really care whether this is true or not is because this is not a physics course, right? What we're going to take away from this is that it is perfectly fine to pretend that gravity is communicated by little emitted gravitons that are constantly being created and hurled outward by mass. Because if you do, all the algebra works exactly as it should. So let's go ahead and think about gravity that way. It's perfectly harmless for our purposes. Okay. All right, and it does end up being valuable in the reasoning that we're able to write down. So what I want to talk about now is this algebra right here. Ultimately, none of this is really that big of a deal, but let's take it little bit by little bit. First, let me temporarily ignore the common factors in this first equation, common factor of negative 4 pi g. I'll come back to that in a minute. Ignoring that common factor, mass, triple integral of density, dV, old news. Right, what I have in purple there, old news. Everybody all right with that? Multiplying on both sides of the equation by negative 4 pi g, not at all controversial. Perfectly allowed to multiply on both sides of an equation by the same factor. All right, now why, though, would I want to multiply by negative 4 pi g? And it is because of the following. There is a relationship between mass and flux. And this relationship is just a kind of a matter of writing it down. It's not that big of a deal. If you have a certain amount of mass, that will tell you what your gravitational field is. Right? And there are certain constants. In the K, what's in the K, it's just details. But given a mass, you can write down exactly what that gravitational field is, and given the gravitational field, you can write down exactly what the corresponding flux is that results. And an easy example is to just consider a sphere. You can just write down the vector field, the radial field vectors are perpendicular to the surface, so the normal dot product is 1. It's a pretty straightforward calculation. And the punchline is, given a certain amount of mass, the resulting flux is this. The flux is proportional to the mass, and the proportionality constant is this negative 4 pi g, which is why I had multiplied both sides of this top equation by negative 4 pi g. Okay. All right. So, is everybody okay with this equation, I believe? And is everybody okay with this equation? Again, don't worry about the specifics of the constant. That's just details. Okay. All right. Now, what else do I know about flux? Well, I know the divergence theorem. There you go. Boom. Divergence theorem. So altogether then, and this is a little bit strange, but if I look at this right here, starting on the top right and then moving sort of counterclockwise as we've just kind of argued through, what I get then is that these two integrals are equal, and of course this is true for any solid. And that means that these two integrands must be equal. So this is actually a really surprising is the wrong word. This is a really awesome result. Let me explain how powerful this result is. Let's suppose that I didn't know this. Let's suppose that I had a distribution of mass. Mass was distributed in some weird way, whatever. Lots of particles of mass then. Individual particles distributed over some significant region of space. Oh my. Well, knowing that distribution of mass, how would I compute the gravitational field? Well, each particle in this huge distribution of mass, each individual particle is creating its own gravitational field. And they're centered in different locations. Of course, each one is centered where that particle is. So you'd have this very complicated kind of infinite summation of a bunch of individual gravitational fields, and it would be preposterously difficult to write all that stuff down. Really hard. And then to compute the divergence of it, oh, well, my gosh, I'd have to kind of work out all of that infinite summation of gravitational fields and then start taking various derivatives. That would be a hard calculation. What we have here is a much simpler way to compute that divergence. You want to compute the divergence of a gravitational field? No problem. What's the mass density where you're looking? Okay, multiply by this constant. Boom. There's your divergence. It's just a snap. Much easier. Okay. All right, so the thing that makes this work, aside from a couple other observations, is, of course, the divergence theorem. So the divergence theorem, very, very valuable tool in studying gravity, which, of course, is, in some contexts anyway, a big deal. Now, you may be thinking to yourself, all right, fine, I'm not going to be a cosmologist or an astronomer. So, I plan on staying on the surface of the Earth for my entire life. So gravitational field's just a constant. That's pretty easy to deal with. Why do I need to understand this stuff? And an answer to that question is to think about electric fields, which I know are a different physical thing. But here's the thing. Electric fields are also inverse square radial. Structurally then, electric fields look just like gravitational fields. which look just like photon flow fields, in other words, light fields. Right? So these other examples up here, which, you might think to yourself, whatever, I don't deal with complex arrangements of light bulbs, and I don't have to worry about complex gravitational situations. Well, yeah, but if you're an engineer, you're absolutely going to need to understand complex electric fields, because, well, it's just a big deal in a lot of engineering. Right? And the best way to think about electric fields, in my opinion, is to think about them being morally gravitational fields. Gravity is an easier thing to think about. Let's think about the players involved in talking about gravity. Mass is very relatable. Density, very relatable, right? Gravitational fields itself. I walk around all day, every day, dealing with the difficulties created by gravitational fields, right? We just have tremendous amount of intuition for most of the players in this conversation. Whereas, let's look over here at this analogous argument concerning electric fields. Electric charge is so non-relatable in sort of everyday physical macroscopic experience that humans didn't even know it was there until a couple hundred years ago. This is not the kind of thing that you just see in your everyday life. It's weird. Likewise, charge density. Likewise, electric fields. Basically not understood at all until a couple hundred years ago. They're almost invisible. You basically never see them in real life. Right? So, my advice, the way I always understood electric fields back when I was, huffing through a second major in physics, was I just always think about gravity. It's just a different kind of gravity. That's the way I thought about it. Right? So, all of the ideas that we did up here, we can apply down here. There's a different constant involved in the field, so of course we're going to get a different constant to deal with, but it remains that quantity is an integral of density dV, now charge instead of mass. Charge creates flux. Flux follows the rules of Gauss's divergence theorem, and so again we get a nice result about the divergence of the electric field and how that's just proportional to charge density. So, by the way, in case you haven't already noticed, this is one of Maxwell's equations. You may also have noticed, conceivably, this also one of Maxwell's equations. In fact, we usually say that these are the same of Maxwell's equations. These are basically the same equation. They don't look like it at a glance. They seem to be about different things. But if you think about it as follows, it's easier to see this. This first equation on the left says charge is proportional to flux. On the right, it says charge density is proportional to flux density. Right? Another great reason to think about divergence as flux density. The unification of these two equations being morally equivalent, all the easier to understand if you think of divergence as flux density. Okay, let me pause. I said a bunch of stuff there. Who's got a question for me about any of that? Feel free. Is everybody all right? Okay. All right. If you are going to be taking an E&M class at any point, I think you're going to find that understanding the divergence theorem, as you will hopefully by the end of this class, will give you a huge advantage over other students taking E&M who might not understand that, because it allows you to see, the divergence theorem is the tool that allows you to see the connection, the relationship between these two equations. So, big advantage. A nice thing. All right. Okay, that's all the physics we're going to do today. I'm going to move on now and talk about Stokes' theorem. This is another one of these analogous to many of the past theorems that we've talked about. You're going to notice the structure of what I've written down here. We'll start off by talking about boundaries and orientations, and then we're going to talk about accumulation, and then we're going to talk about density. Same pattern that we did for several previous theorems. We did it for the divergence theorem last week. We did it for Green's theorem before that. In a way, that this is how I approach the fundamental theorem of line integrals, the fundamental theorem of calculus. So same structure of argument, just different details for a different context. So what is our context here? We're going to be looking at surfaces in space. Okay, we haven't talked about surfaces in space in terms of these accumulation arguments yet. All right, so in particular, you know what? I regret my color choice there. Let me do this in blue. Try this again. We're going to do this in blue. Our surface here. Let's talk about the boundary curve. I don't know why my stylus is so weird. I'm sorry about that. Boundary curve, of course, is that right there. Just imagine a surface like this, right? And the boundary curve is, well, it's the edge. It's where, way I like to think about the boundary of a surface is imagine there's an ant walking around on the surface. The boundary is where the ant gets confused. And he's like, hey, wait a minute, there's nothing over here. He's got nowhere to put his feet, right? Ants couldn't care less if they are going vertically or even if they end up going upside down, whatever. They don't care, right? But they're going to get confused when they get to the edge and there's nowhere to go over in that direction. All right. So, what about orientations? Keep in mind, we're doing vector calculus. That means curves and surfaces are all oriented. That means that this surface that we're starting with itself has an orientation. An orientation on a surface is a normal vector indicating the appropriate direction through the surface, what we consider the positive direction through the surface. Given that orientation on our surface, the question is, which should be the proper orientation on the boundary curve? Should it be that way or should it be this way? What's the correct, what is what we call the induced orientation, that way or this way, on the boundary? Everybody see the question? So, this is another convention. It's arbitrary. Well, as I've described in other circumstances, it was arbitrary 150 years ago, and once this all kind of got settled and the standards got set, it's now not really arbitrary anymore. Now it's the standard. In the same way that we view electric charges, right? Electrons are negatively charged, protons are positively charged. It was an arbitrary choice. They could have gone the other way with it, but they didn't. But it's the standard, and it's really not optional. But it was arbitrary, but it's not up for discussion, right? So same thing here. There is a standard, arbitrary but standard choice as to what that orientation is. And here's how it works. It works off of your right hand. Put your thumb pointed in the direction of your surface normal, right? The surface comes with an orientation. You put your thumb in the direction of that normal, defining the surface orientation. Right hand, very important. It's got to be your right hand. Notice that your finger is bending the way fingers want to bend. Kind of define what I'm going to call a swirl going around the normal vector. Now, this is why it's important that we be talking about the right hand, right? If I were to use my left hand, the swirl would go the other way. And we have to be on board with the convention of those two choices. The convention is the right hand. That swirl then sideswipes along the boundary in the direction that defines what we're going to call the induced orientation on that boundary curve. That's the rule. That makes sense? Okay. Okay, so very importantly, notice that you have to imagine a normal vector here to your surface that is near the boundary, not on the boundary. Can't be on the boundary because we need to be able to define a swirl around the normal vector, right? So that swirl going all the way around the normal vector can then sideswipe up against the boundary. Okay. All right, that's the convention. All right, now let's talk about accumulation. This is what makes it all work. This is the kernel of it all. It's a lot like Green's theorem, in which you'll recall also Green's theorem, the accumulating quantity, was circulation, boundary circulation. Here we again are looking at boundary circulation, just like with Green's theorem. Why is this any different, in fact, at all than Green's theorem? Well, because Green's theorem was exclusive to 2 dimensions. Green's theorem was strictly 2-dimensional. Here we're talking about boundary circulation around the boundary of a surface sitting up in space, right? So the curve itself is also a curve in space. So you can think of what we're doing here as developing effectively a kind of a 3-dimensional Green's theorem. A reasonable way to think about it. Okay. So I claim that boundary circulation accumulates. Now, arguably, we've already made this argument. Right? I mean, we drew a picture along these lines when we were talking about Green's theorem. So I'm going to be quick to justify this because it's morally equivalent. It's a little different. It's 3-dimensional instead of 2-dimensional. But the thing that makes this work is really the same. So here we go. Let's suppose we have a surface, and we have an orientation on that surface. Keep in mind, an orientation on the surface is defined by a consistent set of normal vectors defining the positive direction through that surface. This being the orientation, thumb, fingers, swirl, sideswipe, and all that defines a boundary circulation that would be measured like that. Now let's think about the pieces. Let's think about the left piece. Once I've sort of cut it in half there's the left piece. Again, thinking about the normal vector. Again, swirls and sideswipes and all that. I kind of made a mess there. But there's how you would represent the boundary circulation on the left piece. Now we do the same for the right piece. Like so. And we have to ask our usual question, is green plus blue equal to purple? Right? And mostly, right, you can see there's a lot of cancellation, everything cancels except for these 2 pieces. This would seem to be the problem. This would seem to be the impediment to claiming that this is an accumulation. But then we realize that these 2 little bits of line integral, they're both computed over the exact same curve, but with opposite orientations, which therefore cancel. And that green line integral, that blue line integral are exact negatives of each other, so their sum is 0. And with everything canceling, the whole is the sum of the parts, and therefore boundary circulation is an accumulating quantity. How are we doing on that? Does everybody recognize and notice that this is morally equivalent to the, really, really similar argument we made for Green's theorem? Okay. So a lot of the rest of this goes exactly the same. Boundary circulation, even though we view it and measure it as being along the boundary, that doesn't mean that it's actually happening there, and we certainly don't have to view it as actually happening there. That whole boundary circulation is the sum of the boundary circulations that are happening over little pieces. If you were to look at all the little pieces here and look at their boundary circulations, right? And then if you were to add up over all of these green regions, add those all up, you get the whole. So, yeah, sure, you measure boundary circulation on the boundary. That's the name. But I want to encourage y'all to think of boundary circulation as being distributed over the surface. It's distributed over this thing whose boundary we're talking about. It's distributed over what you might call the interior. Just like every other accumulating quantity that we've talked about. Does that all sound familiar and plausible, maybe? Believable? Okay. All right, and with that, we can talk about density. If we have this quantity that we think of as distributed across area, then we can ask very reasonably how much of that quantity distributed across areas, that quantity being circulation, how much of it is there per unit area? The quantity in question being circulation, we call this circulation density. All right, so it's this morally equivalent to, we talked about circulation density in the two-dimensional Green's theorem context. We talked about flux density in the three-dimensional Gauss context. We talked about change density in the fundamental theorem of calculus context, right? Same idea. It's accumulating quantity per unit size, and quantity per unit size times size gives you quantity. Right? So it's just literally a density in the usual sense of the word. Okay, now with that said, here's the formula for circulation density. It's this right here. It's the curl of the vector field dot the orientation unit normal for the surface. That's the formula. Now, again, I'm not going to compute this. In the same way, I never gave y'all an argument in which I actually derived the formula for divergence, and I never derived the formula for Green's operator, et cetera, et cetera. Why? Well, because it takes a little time, and it's ultimately, while it's an important computation, it's not what I'm going to call intuitively illuminating, right? I think the intuition that's important comes from what I've got up here. What you should think of this as doing, what role that this thing plays, is that it's telling you circulation per unit area. That's really the big idea, what I most want y'all to know about that formula. How to derive it is details, and yeah, it's important, but it's not. If you were to forget how to derive it, that's okay. If you forget what it means, that's not okay, right? This is what you're really going to be using of the idea of circulation density. Okay. All right. Now there is something weird about this. It depends on the vector field. This part is pretty clear. You can see the vector field in the formula right there. Green's operator is computed from the vector field. Divergence is computed from the vector field. The fact that this expression depends on the vector field is not surprising. This is expected. This is sort of what it, of course, ought to be. The weird part here is that it also seems to depend on the surface, because after all, it's the surface and how the surface sits in space. Right? You look at my hand here being a little piece of surface. This normal vector is what describes how my piece of surface is oriented in space. So that's a little weird. Flux density does not depend in any way on the surface or orientation or anything. Purely a function of the vector field. Green's operator, only the vector field, no dependence on the area. So seeing circulation density here all of a sudden depend on the surface orientation is a little concerning. Seems to be outside of the pattern that we've noticed so far. I'm going to come back and we're going to talk about this later. For the moment, let me just say this is not a bad thing. We will make sense out of this, but we will make sense out of it later. All right, we're ready to put it all together. Is everybody okay so far? All right. Here we go. Here's Stokes' theorem. Let me walk you through how to put the pieces together. We've talked about boundary circulation as being a quantity of interest. I'm going to give it a name. We're going to call it lowercase Greek letter sigma. That quantity is an accumulating quantity. The whole is the sum of the parts. So that's what that says. And looking at a part, looking at a little piece of circulation, boundary circulation, I can relate this accumulating quantity, I can relate to size by way of accumulating quantity per unit size, right? So here's our, again, circulation density. This is circulation per unit area. This is the thing that you multiply by area to get circulation, right? All saying the same thing. So all I've done then is just make the observation that, one piece at a time, these things are equal, and so this boundary circulation is equal to this integral. That's the same three-step sort of process in some sense that we wrote down for all of our previous boundary theorems. And the one little twist I am going to do here, and we did not see this with Green or Gauss or fundamental theorem of calculus, but I'm going to go ahead and observe that, check it out, in ds. How about that? We've seen that little combination before. We have previously decided that it was convenient to call that the ds vector. So I'm going to go ahead and make that rewrite, and then here's then our Stokes' theorem, as I tend to prefer to write it like that. All right, everybody cool with that? Let's see it in action. Let's do an example. I'm going to give you my usual warning. Remember, all of these theorems come at a cost. There's always a catch. There's always a, but, kind of an asterisk. Here, the asterisk. You cannot use this theorem to compute just any old line integral that you want. Notice, importantly, but very visibly, explicitly says boundary. Right? Stokes' theorem is only about boundary circulations. I mean, that's, after all, the accumulating quantity in question. Boundary circulations. Right? So, if you are interested in computing a random line integral, where your curve is not a boundary, there is no Stokes' theorem. There's no Stokes' theorem at all. Right? And I emphasize, it's not that Stokes' theorem isn't true. It's that there is no theorem in the first place. Because, think about it. I mean, if, let's suppose you had a curve that was not a boundary. If it's not a boundary, then there is no surface whose boundary is that curve. And if there is no surface, then there is no flux integral to be computed. Right? So again, it's not that, these things will be different if it's not a boundary. No, it's that there is no flux integral at all to even be entertained. Very importantly, only boundary circulations. Okay, all right, with that in mind, let's do our first example. Here we go. The question here, given a curve, given a vector field, let's compute this line integral. Right, vector field given curve parametrized. First thing I want to say about this example, notice in the statement of the question here, notice it does not say, hey, check it out, that curve's a boundary. It doesn't say that at all, right? That's part of the challenge of the question, is to recognize it. to even know to entertain the question of whether this curve might or might not be a boundary. That's part of the student's responsibilities, to know to ask that question and to think about it and to ascertain whether this curve is or is not a boundary. Notice also in the statement of this question, it doesn't say anything about Stokes' theorem. Right? So, just another FYI. I mean, now, on homework exercises, you can kind of, if the homework exercise comes from the section on Stokes' theorem, it's probably a Stokes' theorem question. Context kind of gives it away. Right? On an exam, no such luck. Right? So you have to think about, well, how would I know that Stokes' theorem is the thing to do here? Right, and that's another thing we'll talk more about later. But for the moment, let me just point out, there's a short list of theorems that we have that involve line integrals. Fundamental theorem of line integrals is one of them. Turns out there is no anti-gradient in this case. Y'all can think about why there's no anti-gradient, the little calculation that can be done there. Think back to the Chapter 6 tools that we have, the local test for anti-gradients. It's going to fail here. So, fundamental theorem of line integrals, reasonable thing to think about, dead in the water. There is no anti-gradient. Okay. Is my curve a boundary? That's what would decide whether or not we can apply Stokes' theorem here, right? I need to know whether or not the domain is a boundary. So here's what I'm going to observe. This parametric curve, other than this minus sign, that's our sort of standard unit circle in the xy plane, right? Cosine comma sine. Z is 0, right? And we know exactly what that standard circle in the xy plane looks like. What does that minus sign do? That minus sign just reflects over the x-axis because it puts a minus sign on the y-coordinate. So if our sort of standard circle in the xy plane would have gone around kind of that way, right? The reflection of it, which is what I'm looking at here, it's just still the unit circle, but just going around the other way. Anybody see that? All right, so there's our curve. 0 to 2 pi, so it goes all the way around. And now what do we notice about this curve? Good news. Easy to observe that curve is a boundary. It's the boundary of this, what I'm calling the surface S, in yellow there. And now we do have to wonder about orientations, right? It's tempting to say, whoa, this, no, isn't it supposed to go around the other way? Doesn't it have to go, doesn't the region have to be on my left? Remember, that's a 2-dimensional rule. Right here we're in 3 dimensions, we have different rules for how orientations work. All I need here is that my surface have a normal vector that makes the whole fingers and swirls and side swipes thing work. So let's think about whether or not we can make that work. And let's see here, I'm kind of messing up my picture here. There's my orientation on my curve. Let's see here, I'll use orange. This would be fine. There's 2 possible orientations. Here's the good news. Because there are only 2 possible orientations on my surface, I can just kind of try them one at a time. I don't have to have a method for reverse engineering my orientation rule, my boundary orientation rule, which presumes that I know the surface orientation and tells me how to infer the boundary. Here I need to go the other way. I have the boundary orientation. I need to sort of reverse engineer what the surface orientation is. So I advise just identify your 2 options and just try them both and see which one works. One of them is going to work, one of them is going to not work. So just try. Looking at our first option here, I'm going to deliberately take the one that's wrong so we can see how it fails. Thumb, fingers, swirl, side swipes. Gives us There's my swirl. There's the side swipe, and notice it's just wrong. Right? That induced red orientation that comes from this speculated upward surface normal, it's just wrong. It needs to go the other way. All right, so no for that one. Let's see. Oh gosh. Okay, there we go. Okay, now let's try the other one. Let's try downward as my surface orientation. The process of elimination, I kind of know this has to work, but okay, thumb in the downward direction, right hand, fingers defining a swirl that is like this, which gives me an induced orientation like this, which is correct, right? So this surface orientation induces the correct orientation on my boundary curve, and therefore with this downward surface orientation, indeed this is a boundary. And I'm out of time. Shoot. Okay. Well, we'll pick up here on Wednesday. Y'all have a good one. See you later. Don't forget to stick around and make sure I mark you for attendance. Otherwise, see you Wednesday.